Good morning, students. Welcome to Bindu Dhadwal chemistry lessons. Our topic for today is alkenes. Alkenes are unsaturated hydrocarbons having at least one carbon-carbon double bond. The general formula, because of the presence of double bond, there will be two hydrogen atoms less. So the general formula will be CnH2n. Two carbon atoms are less because of the double bond. For alkanes, the formula was CnH2n plus 2. For alkenes, 2 will be missing, so the general formula will be CnH2n. These are also called olefins, meaning oil forming, because the first member of these compounds, ethene, forms an oily liquid on reaction with chlorine. Next is structure of double bond. So carbon-carbon double bond in alkenes consists of one strong sigma bond and one weak pi bond. The strong sigma bond with a bond enthalpy of 397 kilojoules per mole is formed by the head-on overlapping of the sp2 hybridized orbitals of carbon, whereas the weak pi bond is formed between the sidewise or lateral overlapping between the unhybridized p orbitals of the carbon. This sidewise overlapping occurs perpendicular to the planar sigma bond formation. So the bond enthalpy is 284 kilojoules per mole, which is weaker than that of sigma bond. The carbon-carbon double bond or pi bond is shorter than the carbon-carbon single bond. Double bond length is 134 picometer, whereas single bond length was 154 picometer. Because sidewise overlapping results in a poor or weak pi bond, this makes alkenes behave as a source of loosely held mobile electrons. Because of presence of loosely held electrons, alkenes are easily attacked by reagents or compounds which are in search of electrons. Such positively charged substances are known as electrophiles or electrophilic reagents. The presence of weaker pi bond makes alkenes unstable molecule in comparison to alkanes, and thus alkenes can be changed into single bond compounds by combining with electrophilic reagents. The strength of double bond is more than that of carbon-carbon single bond. In ethene, the bond enthalpy of the double bond is 681 kilojoules per mole, whereas in ethane it is 348 kilojoules per mole, less than that of double bond. So here are the diagrams. This diagram is an orbital picture of ethene depicting the sigma bonds only, and this diagram shows how the unhybridized p orbitals are undergoing lateral overlapping to form the pp pi bond. And this diagram shows that the pi electron cloud lies above and below the planar C2H4 molecule. Here we can see the parameters of the compound alkene. The double bond length is 134 picometer in comparison to single bond 154 picometer. Carbon hydrogen bond length is 110 picometer. Bond angle is 116.6 degrees for hydrogen-carbon-hydrogen bond and 121.7 for hydrogen-carbon-carbon bond. Next is nomenclature of alkanes. So for giving Iupac name to the compound, we select the longest chain containing the double bond. When we have selected that chain, then we do numbering of the chain in such a manner that numbering is done from the end which is nearer to the double bond. And after naming the substituents and the word root, the suffix "ene" will replace "ane" of alkenes. For example, In case of C2H4, the name will be eth for 2 carbon atoms and ene for a double bond. In case of 3 carbon atom compound, the name will be propene. And the first member CH2, according to the general formula CnH2n, when n is equal to 1, is CH2, but this compound is unstable, so the first stable molecule is ethene. Then the next compound will be called propene. The next compound, this compound, we start the numbering, select the longest chain, 1, 2, 3, so 2-methyl prop 1-ene. This compound is but-1-ene. We start numbering from this end. This compound is but-2-ene. Then next compound is, numbering is done from this end. So this is 3. So 3-methyl but-1-ene. This compound will be known as buta-1,3-diene. So this is how IUPAC name is given to the compounds. So based on these rules, we can write down the IUPAC names of the following compounds. For example, this compound consists of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbon atoms. So word root will be dec. To write down the IUPAC name of this compound, we first expand the molecule. On expansion, we see that double bond is closer from this end. So numbering, we will start from this end, 1, 2, 3, 4, 5, 6, 7, 8. So the name will be 2,8-dimethyl, then 3,6-deca-diene. And again, in this case, we will start numbering from this end. So we get 8 carbon, 1, 3, 5, 7 octa-tetraene. Similarly, using the rules, we can write down the names of these compounds. We can also calculate the number of sigma and pi bonds in the above structures. For example, in this particular structure, when we write down the number of atoms, we know that all carbon hydrogen bonds are sigma bonds, and of the double bond, one bond is sigma and one is pi. So calculating, we get 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 and to 17 sigma bonds and 1, 2, 3, 4 pi bonds. So this is also one of the commonly asked question in case of alkenes. Name the number the sigma bonds and pi bonds in a molecule. Next is isomerism in alkanes. Alkanes can show two types of isomerism when difference arises on account of structure of compounds. It is called structural isomerism, and when difference occurs on account of geometry of the compound, it is called geometrical isomerism. First two members, ethene and propene, have single structures, but compounds like butene onwards, they have more than one structures. For example, the different structures of butene can be a 4-carbon chain with double bond on first position, then second double bond on second position, and third is a 3-carbon chain with double bond on the first position. So out of these, the structure 1 and 3, these are chain isomers because the difference occurs on the count of chain. Similarly, 2 and 3 are also chain isomers. Then compound 1 and 2 can also be called position isomer because here the difference in the two compounds occurs on the position of double bond. In first case, its double bond lies at carbon atom number 1, whereas in second case it lies at carbon atom number 2. So these are position isomers. So structural isomerism can be divided into two categories: chain isomerism and position isomerism. In the double bonded carbon atoms, in order to satisfy the two valencies of the double bonded carbon atoms, you can write the groups to which these carbon atoms are attached in two different manners. If the two groups are different from each other, then in that case, the two structures arise. One where the two same kind of groups lie on the same side of double bond, and the other where the same type of groups lie on opposite side of the double bond. Now, unlike alkanes where the single bond could be rotated very easily, there was free rotation about the single bond. In case of double bonded compound, rotation about double bond is hindered. It's not possible because the bond breaks while rotating this bond. So this structure cannot be converted into this structure. So we see in actual practice that there are two different kinds of compounds with the same molecular formula but having different geometries. So this compound in which the alkyl groups of this, in which the substituents of the same kind are present on the same side of double bond are called cis isomers. And the compounds where they are present on the opposite side are called trans isomers. So they have different geometry. So such groups which differ on account of their arrangement in space are called stereoisomers. And presence of stereoisomers occurs because no rotation is possible about the carbon-carbon double bond. So these two will have different geometries, so they are also called geometrical isomers of each other. For example, if we take butene, so two possible geometries are possible. One where the two methyl groups across the double bond are present on the same side of double bond. This is called but2ene. The other where the methyl groups are present on opposite sides of the double bond. Such kind of a compound is called trans-but2ene. So we place the prefix to show the geometry of the compound in front of the name of the compound. Now, these have the same molecular formula, but they have different physical properties on account of their different geometries. For example, cis-but2ene has a boiling point 277 Kelvin, higher than that of trans-but2ene, which is a boiling point 274 Kelvin. They also have different dipole moments. In case of cis-but2ene, the two polar bonds are arranged in such a way that because dipole moment is a vector quantity, the net dipole moment of the molecule will be the vector sum of the two vectors. So on addition, we find that there is a net resultant of the dipole moment which is of the order of 0.33 dB. So because it has a dipole moment, so it is polar in nature, and because it's polar in nature, attraction is more, and so its boiling point is more. In case of trans-but2ene, this bond is polar, but its dipole moment is cancelled by the opposite bond because its dipole moment of the same magnitude is just opposite to it, and the two cancel each other. So the net dipole moment is 0 dB. Because two methyl groups are in opposite direction, so their dipole moment cancel each other, and so their boiling point will be less because they are non-polar in nature. So that's all in today's video. If you like the video, please do share and subscribe. Thank you. Have a nice day.